This lesson is factoring quadratic expressions part 2. So in example 1, we're factoring a trinomial, but in these problems, the lead coefficient, which we can see here is used with the variable a, it's not equal to 1. Notice in part A, it's a 3, and in part B, it's a 2, and part C, it is a 6. The first step, though, however, is the same, where we are going to begin by multiplying A and C together, and we put that number on top of our puzzle, and then we put B on the bottom. So we'll find the two numbers that multiply to the top value and add to the bottom value. But then from there, we're going to have some new stuff that we haven't seen yet. So in part A, to set up the puzzle and get started here, we can multiply 3 and 5. So 15, and then the number 8 goes on the bottom. So what multiplies to 15 and adds to 8? 5 and 3. All right, now notice we cannot just simply say, okay, x plus 5, x plus 3, there's our answer, we're done. The reason is if you can check that by just foiling, and you notice if you foil, you get x squared plus 8x plus 15. That is not what we started with. We have a 3 in front of the x squared, which means if we just think of guessing and checking, one of these x's have to have a 3 in front. Now you can't just put a 3 there, though. We have to figure this out. So one way that will work to do that is to take the lead coefficient of a, which is a 3, and divide each of these numbers by 3. After you do that, you have fractions now. And if the fractions can be reduced, you want to reduce them next. So 5/3 cannot be reduced. We leave that how it is. 3 over 3 can reduce to 1 over 1. Okay, now you have a numerator and a denominator of each fraction. You take the denominator, the number on the bottom, so I'm going to highlight that in each fraction. You multiply that number times x, and then you add the top number. So some teachers call this bottoms up. Okay, you take the bottom number times x plus the top number. So with a 1 over 1, I get 1x plus 1. And there's your answer. So you can check this by foiling, just like before. If I were to foil, I'd get 3x squared plus 3x plus 5x, which combines to 8x, and then a plus 5. All right, so to add to this little chart up at the top here, we find the two numbers that multiply at the top, add to the bottom, and then we divide by a, and then we reduce, and then we do bottoms up. Okay, bottom times x plus the top. So let's practice this with a couple more examples. Part B, I set up my puzzle with 2 times negative 21 on top. So it's negative 42. And on the bottom, I have a negative in front of p, which would be a negative 1. So I need two numbers that multiply to negative 42 and add to negative 1. If you'd like to make your list of factors, go ahead. You can list 1 and 42. You can list 2, 21. You can list 3 times 14. 4 doesn't work, 5 doesn't work. You have 6 times 7, and that's our entire list. Now, if you can just look at this and right away know to get a 42 to be negative, you'd have a positive 6 and a negative 7, so that those two numbers also add to negative 1, then you don't need to make that list of factors. But if it helps you to make that list and you can use your calculator to do that, then feel free. All right, so don't forget now, once I found these two numbers, I look at my a value, which is a 2. So I divide by 2, divide by 2. Negative 7 over 2, we're done. That does not reduce at all. But the 6 divided by 2 reduces to 3 over 1. So now that I have my two fractions reduced, I can set up my two sets of parentheses. I'll start with 3 over 1. I take the bottom, which is a 1. I times that by x, which is just x, and then I add the top, which is 3. So x plus 3. Over here, I take the bottom times x, so 2 times x, and then minus 7. There's my answer. You can check your answer here by using FOIL. Same thing on part C. So if you want to try this one on your own, go ahead and hit pause, try part C, and then hit play to check your answer. All right, let's see how we did on part C. 6 times negative 4 is negative 24. 5 goes on the bottom. Let's see what multiplies to 24. I'll make a list real quick. 1 and 24, 2 and 12, 3 and 8, 4 and 6. To get a 5, I know the difference of 3 and 8 is 5, so I'll be using those numbers. But which is positive, which is negative? Well, I want to add to a positive 5, so the 8 is bigger. That has to be positive. 3 is negative. Okay, now I take these and divide both by 6, because 6 is my lead coefficient. It's my a value in front of the y squared. Both these fractions can reduce. So to reduce 8/6, I can divide 2 on top and divide 2 on the bottom to get 4/3. And negative 3/6 reduces to negative 1/2. Now using 4/3, I start at the bottom times x plus the top. And then negative 1/2, I take the bottom times x plus the top. So this would be a 3x plus 4 times a 2x minus 1. Now, if you're getting help from someone else, or if you're watching videos on YouTube or any other resources you may have, to textbooks, there are lots of different ways you can factor these trinomials. But this is the way that we chose to initially teach it. And during our Google Hangout, we can go over other methods if you would like to see those. All right, the last part for today then, to move on with factoring here, is factoring when we have special patterns, and we're going to focus on a difference of two squares. So a difference of squares is when you have a perfect square minus a perfect square. So the difference is because there's a minus, and squares is short for perfect square. A perfect square is when you have something squared. Now, if we think of numbers, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and so on, you can make a list of perfect squares. Let's keep going to list the first 10. So after 25, 6 times 6 is 36, then 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. So one nice thing about a difference of squares is, first of all, there's only two terms. So if there's no GCF, then you know when there's two terms, you can do difference of squares. When there's three terms, you can set up the puzzle like we did in the first example. All right, so, another thing is if you recognize any of the numbers from this list, then it's most likely difference of squares may help you out there, as long as there's a minus and everything is perfect squares. So with our example, x squared minus 9, this is a perfect square, because how do you get x squared? By doing x times x. 9 is a perfect square. How do you get 9? 3 times 3. And when we're factoring a difference of squares, we will always have 1 plus sign, 1 minus sign. And let's see how when we FOIL this, it'll get back to what we started. X times x is x squared. When you have your minus 3x and your plus 3x, those just cancel each other out. And then 3 and negative 3 is a negative 9. So this only works when it's a difference and two perfect squares. If you had x squared plus 9, you cannot factor that. Okay, so x squared plus 9, there's no way to factor that at all. You cannot do x plus 3x plus 3, because that would be x squared plus 6x plus 9 if you FOIL it to check it. So it only works when you have a perfect square minus perfect square. All right, so once you kind of get the hang of this, it's a similar pattern each time, and these problems go pretty quickly. There's not even really any work to show. With x squared minus 49, I have a perfect square minus a perfect square. I know to get x squared, I use x, and I know to get 49, I use 7 times 7, and I put 1 plus, 1 minus. And the order of the plus and minus can go either way, so you could put x minus 7 first, and then x plus 7, same answer. Either of these would be correct. All right, x squared minus 16, see if you can try that one. Go ahead and hit pause, write down your answer, and then check it. So in this one, we should have x plus 4 times x minus 4. Remember, the first thing you're doing is looking for a GCF, but there is no GCF. Then you notice there's two terms, so you can factor a difference of squares. All right, part C. This has a lead coefficient. However, that is a perfect square, and so is the 81. So there's still no work involved here. We know to get 16y squared, we can do 4y times itself, 4y. To get an 81, we can do 9 times 9, and we have 1 plus, 1 minus. Last problem, part D. Let me switch colors here. This time, 18 is not a perfect square, and neither is 2. But remember your first step anytime you're factoring. You should always look for GCF. If I take away GCF of 2, I'm left with a squared minus 9. And now if I look at that binomial in the parentheses, it is a difference of squares that can be factored further to a plus 3, a minus 3. Don't forget the 2 in front. There is our final answer. So what I'm going to do really quick before we conclude this lesson is to just summarize the steps for factoring. Anytime you need to factor a problem, what are you going to do first? You're going to look for a GCF. What are you going to do second? You're going to look for the number of terms. Is it a binomial with 2 terms, or is it a trinomial with 3 terms? If there's 2 terms, see if it's a squared minus b squared, a difference of squares, where you can do a plus b times a minus b. And that's what we did in all the examples above. If it's 3 terms, ax squared plus bx plus c, then you set up your puzzle with a and c on top, b on the bottom. You find those 2 numbers, you divide by a, and you do bottoms up. So this concludes our lesson on factoring.